Alrighty, in this video here, we're going to talk about 3 measures of position. So our third objective is to identify the position of a data value in a data set using various measures of position, such as percentiles and quartiles. So this is the part that we saw in the calculator that I'll tell you a little bit more later down the road. We've now made it later down the road. So measures of positions are used to locate the relative position of a data value in a data set. So a value at the 88th percentile has 88% of the data values below it and 12% of the data values above it. So the median is a measure of position corresponding to the 50th percentile. So since the median is the middle number, it's the 50th percentile, meaning 50% of the data is below it, 50% of the data is above it. All right, so that's this kind of positioning there, kind of telling us where we're at. So if you ever get like a test scores back and you're like, oh, I'm in the 80th percentile, that means you are 80% better than the people that took the test, but there's 20% that's better than you. And you kind of look at it that way. So standard scores can be used to compare the position of data values on two different distributions by providing a measure of how many standard deviations a particular data value is from the mean. So we'll call this a Z for now. And it actually has a name. It's called a Z-score instead of standard score. So anytime you see the Z, that's what it means. And it's kind of the same score no matter if it is a sample or population, because it's solved the same way, just has different meaning. So for a sample, it's going to be whatever that value you're looking at minus the mean divided by standard deviation, whatever that is going to give you a Z-score. That Z-score is basically just telling you how many standard deviations away you are from the mean so that we can use the empirical rule to kind of figure out, all right, where do you fall in the percentile to see where you are on the curve to see if you're above or below. Same concept when dealing with population, just the symbols change, but still the sample that you're looking at minus the mean divided by standard deviation. So again, X sample data, X population data. The X bar, again, remember, means sample mean. Mu means population mean. Lowercase s is your sample standard deviation. And lowercase sigma is the population standard deviation. So let's look at example 16. So did a student perform better on a calculus test with a score of 65, having a mean of 50 and a standard deviation of 10, or a history test with a score of 30, having a mean of 25 and a standard deviation of 5? So first we're going to look at the calculus test. So 65 and 30 are both above the mean. 65 is 15 points above the mean of the calculus test, which is 1.5 standard deviations above the mean. 30 is 5 points above the mean of the history test, which is 1 standard deviation above the mean. So the student has a higher relative position on the calculus test because they are 1.5 standard deviations away. So again, the more standard deviation positive you are, the higher in the percentile you are. All right. So now, using that information, now that we know how many standard deviations away each one is, that is pretty much what the Z-score is. So in the second type of solution, we can use Z-score or standard score to determine how many standard deviations above or below the mean data is. So again, what they just said in words in this first solution is this in math sense. They took the number you're looking at, which was 65, minus the mean, which was 50. They got 15, divided that by the standard deviation of 10, and got 1.5, meaning 1.5 standard deviation above the mean. Versus the history test, Z was equal to 30, which is what they made on the test, minus 25, which was the average, divided by the 5 of the standard deviation. So they got 5 divided by 5, which was 1, meaning it was only 1 standard deviation above. Since the Z-score 1.5 is higher than 1, The z-score for the calculus test being larger, so the relative position in the calculus class is higher than the relative position in the history class. So therefore, you actually did make a overall better grade on the calculus because you were just that much better than everyone else in the class. Versus in the history, yes, it was a low mean, but you didn't do as good in calculus versus people in the classroom or who took the test. Maybe the overall test in the maybe it's the AP calculus test and the AP history test or something like that. All right, so talking about percentiles here. So percentiles divide a data set into 100 equal groups, known as the Peak percentile. Is a value in which about P percentage of the data values are less than or for which about 100 minus P% of the data values are larger than. So again, we saw that 88%. So if you're 88 percentile, your 88% of the data is below you, but 100 minus 88 would give you 12. 12% of the data is above you. So again, percentile is simply just the number of values below the specific data value plus 0.5, total number of values in the data set n times 100. So again, when you're looking at the percentile, number of values below, so if you had a set of numbers and you're just trying to figure out what percentile it is, you would have to count how many numbers there are, add 0.5, this kind of helps with the data, divide that by n, and then multiply that by 100. So again, thus P equals the percentile. C will represent the number of data values below a specific data value that you're looking at. N would represent the total number of data values in the data set. And the formula to find it we see is C plus 0.5 divided by N times 100. The formula, though, to find the data value corresponding to a given percentile, so it's a little bit different if I give you the percentile and I want to know what that actual value or how many values correspond to that. You would have to do N, the number of samples in there, times the percentile, divide that by 100, and then you would find out how many numbers are below that percentile. So that's what that C again represents, number of data values below the specific data value. If C, though, is not a whole number, we will round up to the next whole number. So even if it's like 2.1, we're just going to say 3. So that means 3 numbers are below that percentile. Then starting at the lowest value, we'll just count to the number that corresponds to the rounded up value. So we'll go 1, 2, 3. There's our number. So if C again is a whole number, we'll use the value between the C and the C plus first term. So let's say C is 2. Then the one we'll look at will be the 2 and 3. So whatever the number between that is. Values when counting up from the lowest value. So we'll go 2 and 3, so that'd be 2.5, or whatever the number and average of the 2 and the third number is. So let's do that in practice here. So to find percentiles, a teacher gives a 20-point test to 10 students. The scores are arranged in order from lowest to highest. We want to find the percentile for a score of 12. So we want to know what is the percentile of this guy right here. So and then part B, we're going to find the corresponding number that represents 60th percentile. So for solution A, of the C, there is 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 6 numbers. But since we're looking at the value of 12, because again, this is the numbers, again, C, to say it one more time, C is the, where's that? Is the number of data values below a specific data value. So since I'm looking at 12, we're going to go 1, 2, 3, 4, 5, 6, 7. We're going to count that number so we can have the percentile in which all numbers are less than that. So that would be C equals 7. Since 12 is in the 7th position in the ordered list. So if we hit that number, we're going to count it as one of the numbers to find the percentile. There are 8, 9, 10. There's 10 numbers in total, so that's n would be 10. Our p then would equal, again, n plus 0.5 divided by n. I think this is on your work already, but just so we have it all together, see 0.5 divided by n, sorry. So my c then is 7.5 divided by 10, which comes out to, well, sorry, got to multiply that by 100 as well. That comes out to 75%. So I can see that the score of 12 would be in the 75th percentile for the value of 12. All right, and then of course it has it all drawn out for you as well in your notes for you. So again, c plus 0.5 divided by n times 100, we get this result here. So 12 is the 75th percentile. Now, in solution B, I want to know what number represents the 60th percentile. So I know there's 10 numbers. I know my p is 60, so my equation now changes from c equals n times p. So that's 10 times 60 divided by 100, which does come out to 6. Since 6 is a whole number, the percentile is the value halfway between the 6th and the 7th number. So the 6th number was 10, right there, and the 7th number was 12, so thus the 60th percentile will be 11. Had this been a decimal, let's say 6.1, then we would just round up to 7, and it would be whatever the 7th number is. So when you end up with a whole number, you'll go from that number to the next number, find the number in between. But if you end up with a C that is a decimal, by rounding to the next whole number, you've already taken care of that. All right, so that is how to find the percentile, and then figuring out what number is in the percentile. So let's talk about quartiles. All right, quartiles divide the distribution into 4 equal groups denoted by Q1, Q2, and Q3, representing the 25th percentile, 50th percentile, or median, and this 75th percentile. Q4 would represent 100th percentile if you didn't catch on to that. To find data values corresponding to Q1, Q2, and Q3, we want to arrange the data set in order from lowest to highest. Find the median of the data values. That will represent Q2 because it's the 50th percentile. Then we're going to find the median of the data values that fall below the median. That will be Q1. So what we do is we find the middle of the numbers, and then we find the middle of the numbers on the left side. That represents Q1, also known as the 25th percentile. And then if you are at Q2 already, the halfway point, we also want to go on the right side of the median and find the middle of those numbers, and that will represent Q3. I'll also show you again how we can use technology. If you remember when we did that in the previous video, it broke it down by Q1, Q2, Q3, and I'll tell you what that all means. Now I'm telling you. So in example 18, it says find the quartiles of the data set, find the data values corresponding to Q1, Q2, Q3. We'll do this by hand because it's so small, but I'll also show you again how to use the calculator when dealing with larger amounts. So first off, let me just put this all up here. Y'all have the data set with y'all. So I'm just going to put the data set in least the greatest. So that would be 12, 13, 15, 16, 18, 19, 20, 27, and 36. So to find the median or Q2, we need to find the median number, the middle number here. So here we go. I need a different color. It's with orange. So looks good. All right, so that's 1, 2, 3, 4, 5, 6, 7, 8, 9. Remember, 9 divided by 2, that's 4.5. So I just need to go to the 5th number. So 1, 2, 3, 4, 5 right there. And then that tells me I have 4 numbers here, 4 numbers there. So 18 is the median, which is Q2. Now we're going to list the values less than the median itself. So that would be 12, 13, 15, 16. Now we want to find out what is in between this set. So I have 4 numbers divided by 2, so that means I need to find the 2 numbers between 13 and 15, and hopefully you go, well, that's 14. Then we're going to do the same thing on the right side. So this is going to be 19, 20, 27, and 36. To find the middle number between 20 and 27, if you don't easily see it, remember you can do 20 plus 27 divided by 2. So 47 divided by 2. 46 would be 23, so this would be 23 and a half. So I see that my quartile 3 would be 23 and a half. So again, the Q1, 2, 3s and stuff like that don't necessarily have to be an actual value in the data set. We're just trying to find out, all right, where is the in-between all of these data sets? So there you go. So you just found the Q1, 2, and 3 without a calculator with easy sets of numbers. Let's look at example 19. So we're going to find the quartiles. So again, doing this work again. So another example. Again, put these in order. So that looks again. Oh, they're already in order. All right, so that's 14, 16, 17, 18, 19, 20, 24, 31, 32, and 54. Q2, so there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 numbers divided by 2, so that's 5. So that's 1, 2, 3, 4, 5. So I need the number between 19 and 20, which would be 19 and a half. So this right here would be the Q1. There's 5 numbers on each side. So when I want to do things less than the median, I would now include that 19. So that's 14, 16, 17, 18, 19. Now I can see Q1 would just be 17. And then on the Q3 side, it's 20, 24, 31, 32, 54. I can see that 31 is the quartile 3. So they gave you an example of an odd and an even number of lists, so you can kind of calculate what the Q1, 2, and 3 is. So again, pretty easy when it's just an easy set. If it's a large set, like 30 numbers, that could take you quite a while, but just easy as doable. All right, so let's talk about what we call the interquartile range. So the interquartile range, or also known as IQR, is the difference between the third and the first quartile. So to find IQR, we take quartile 3 minus quartile 1. And that's it on that part. So on example 20 here, if we find the interquartile range, to find the IQR for the data set listed in the previous 2 examples, they went ahead and put it in least to greatest for us, since we already did that on our own. We just need to just calculate our Q3 and our Q1, but we already did this. So if we pull our data for the first set of the data, our Q3, so again, define the data set, it's going to be, so I'm going to do IQR one more time. It's going to be Q3 minus Q1. So my Q3 for the first data set was 23.5. And then for my second data set was 14 for the Q1, which then gives me 9.5. So my IQR range is 9.5. And my IQR for the second one would have been 31 minus 17, which comes out to 14. So that just gives us the range of our data between 25 and 75% of our stuff. So remember, the larger that range is, the more spread out our data is. The smaller our range, the more condensed our data values are. Meaning maybe there's just a lot of repeated numbers or just really close together. All right, so we've been talking about this word outliers quite a bit in this chapter so far, so let's finally give it a definition. So an outlier is an extremely high or extremely low data value when compared to the rest of the data values. The mean of the standard deviation can be affected strongly by outliers. So since the mean can be, and the standard deviation is based off the mean, this mean and standard deviation are affected by outliers very strongly. Thus, they are non-resistant statistics, meaning they they're not resistant to it. They get affected by it. The median and the interquartile range are less affected by outliers and are called resistant statistics. So the median and interquartile range is not affected by outliers. It's just affected by if you add or take away more numbers from the set. It's not so much if, because I could add like for instance up here, I could add a 17 and that's kind of be in the middle. So that'll affect it just as much as if you put 71 at the end. It's just going to affect how many numbers there are. All righty, so there we go. So let's kind of review all of the things we've seen so far. So to identify, come on. To identify outliers, we're going to arrange the data in order from the highest to the lowest. Doesn't really matter. You can actually go lowest to highest because that's exactly what we did in the rest of it. 2, we're going to find the IQR, which again is Q3 minus Q1. 3, we're going to then multiply the IQR by 1.5. So once we calculate this IQR right here, we're going to multiply by 1.5. This will tell us the upper outlier boundary. So we do this right here. We'll add it to Q3 to find the lower outlier boundary. We're going to take that result and subtract from Q1. And these two values that we get, if any of our data set is outside of these boundaries, now they're considered what we would call outliers. So a lot of times you'll look at data set and go, man, that's an outlier. But then mathematically, you're like, oh, it falls right inside. So it's not. It skews the data, but it's not an outlier. And then 5, we'll check the data set for any data values not between these boundaries to classify them as outliers. So in this next example, we're just going to determine all of our outliers. All right, so to find outliers, we're going to check the data set for outliers in themselves. So we have 14, 16, 17, it's all nice in order. I love that when I do that. And we've already done this before. This was data set 2. So I'm just going to pull the information from our data set. We got a 17 and a 31. So the first thing we're going to do is find our interquartile range, which is IQR. So this would be 31 minus 17, which is 14. We did this earlier as well. Now, to calculate our boundaries, we also need to determine what this times 1.5 is. So again, to find the lower boundary, you're going to start with the Q1, which in this case is 17. You're going to subtract it from the 1.5 times the IQR of 14. So again, this is going to be Q1 minus 1.5 of the IQR. This will be Q1 there. This would be Q3 plus 1.5 IQR. So when I do the math here, this gives me 17. 14 times 1.5 gives me 21. So this is going to be 17 minus 21, which gives me -4. I then take this Q3, my Q3 was 31, so 31 plus 1.5 times 14, so that'd be 31 plus 21, which would be 52. So any number that falls on the outside of -4 or 52 would be considered an outlier. So when we look at this data, outliers are the data values smaller than -4 and greater than 52. Obviously, I don't have any negatives, so there's no low outlier, but I do have a 54. It is outside of 52, so the outlier here is 54. But I'm telling you, a lot of times you could have had 50. It has to be outside the boundary. So if it lands on 52, it is not considered to be a outlier because it's on the boundary number. So you might look at it and go, wow, 52 is right there. And then you're like, Oh, but it's not, because that's to fall outside of the data values. All right, that would pretty much wrap up 3.3. And then I will then have another one for 3.4. See you in the next video.